Welcome to the Compressible Flow lesson series. This is the first in what I hope will be about 70 videos or so on compressible flow. If you look at the details for the playlist of this video series, you'll see a link to an Excel spreadsheet that contains the videos and also the annotated PDF files that I created while generating each video. Lessons are labeled by their week and a letter, such as O1A, O2B, etc. Typically we'll have about 5 lessons per week. So welcome to Lesson 1A, Introduction to Compressible Flow. In this lesson we'll compare incompressible and compressible variable area duct flow. I'll explain why the beloved Bernoulli equation no longer applies when we're talking about compressible flow. And then we'll start to review some fundamental equations of thermodynamics, which will be necessary to analyze compressible flow. Let's start by looking at flow in a variable area duct. We'll assume steady flow. Suppose we have an expanding duct from cross-sectional area A1 to cross-sectional area A2 with average flow speed V1 at the inlet and V2 at the outlet. This is state 1 and this is state 2. As you know from your fluid mechanics class, conservation of mass for such a duct flow tells us that m dot, which is rho VA, is a constant, where V is the average speed at a cross-section. Another way to say this is that m dot 1 equal m dot 2. If we also take density as the average density in the flow, we can write this as rho 1 V1 A1 equal rho 2 V2 A2. Now let's consider incompressible flow. Since density is a constant, the density can drop out of this equation. And we like to define this grouping of terms, V1A1, as the volume flow rate. We use V dot in our fluid mechanics textbook. Other people use Q. Either way, the volume flow rate is the average speed times the area. I use a capital V with the bar through it to represent volume. That's why V dot is a volume flow rate. And I use V without a bar as the speed or the magnitude of the velocity vector. Since density has dropped out in our equation, V dot 1 equal V dot 2, or V1A1 equal V2A2. This is the familiar steady conservation of mass equation for a duct that we're used to in incompressible flow. And we can see from this equation that therefore, as A, the area goes up, the speed goes down. So in the case of an expanding duct, A1 is less than A2, therefore V1 is greater than V2. Let's consider also the pressures, P1 and P2. For adiabatic flow with no, or we should say always negligible, irreversibilities, for example friction, and irrotational flow, we also have what I like to call the beloved Bernoulli equation, which is P1 plus 1/2 rho V1 squared plus rho g Z1, where Z is the elevation, equal P2 plus 1/2 rho V2 squared plus rho g Z2. This is the equation that all students love to use, which is why I call it the beloved Bernoulli equation. Throughout this entire course, we will ignore the gravity terms. We'll always be talking about gases, where the density is very small and changes in elevation lead to negligible changes in these two terms compared to pressure and velocity changes. From this equation then, without the gravity terms, as speed goes up, pressure goes down, and vice versa. And we can solve this for P2, which will equal P1 plus 1/2 rho V1 squared minus V2 squared. And since V1 is greater than V2, P2 must be greater than P1. This is what everyone's used to, assuming that you've taken an undergraduate fluids class, which is mostly incompressible flow. Now consider compressible flow. You need to wipe these equations we've just written from your memory banks. They no longer apply. Namely, V dot 1 equal V dot 2 no longer applies, and the Bernoulli equation no longer applies. I'll comment here that even if we let rho be rho 1 on the left and rho 2 on the right, it still doesn't apply. You need to take off your incompressible flow hat and put on your compressible flow hat. So what equations do apply? Well, conservation of mass must still apply. That's a very fundamental equation. M dot equal rho VA equal constant in a duct. So this is true even for compressible flow, but by its very name, compressible flow means that density is not a constant. So let's go back and reconsider our expanding duct. With flow from left to right as before, area A1 and A2, but now we also have density ρ1 and density ρ2. In this one-dimensional approximation, where these speeds and densities are averages, we can still write m dot as ρ1 v1 a1 at the inlet 1 equal ρ2 v2 a2 at the outlet 2. This equation still applies. Of course, we're assuming no leaks and we're assuming steady flow. But I ask a question here. As the area increases in this duct, does V go up or down? The answer is that it depends on rho. It can do either. For example, if density increases, ρ2 greater than ρ1, then speed V2 must go down. It must decrease. We see this by solving for V2. V2 equal V1 times ρ1 over ρ2 times A1 over A2. In this case, with ρ2 greater than ρ1, this is less than 1, and this is less than 1 by our geometry, since we're assuming an expanding duct. But if ρ2 is less than ρ1, in other words, rho is decreasing, whereas here rho is increasing, our equation for V2 remains the same, and we still know that A1 over A2 is less than 1 for our expanding duct. But what about ρ1 over ρ2? Well, now that is greater than 1, as we see here. So is V2 greater than, equal to, or less than V1? The answer is any of the above. V2 can be less than, equal to, or greater than V1, depending on how much rho decreases. How do we know which of these is the case? The answer is that we need some equations from thermodynamics. I'll start a quick thermodynamics review here, and we'll have more thermodynamics in later lessons. My notation will be that capital E is the total energy of a system, and little e, lowercase letters in general, is the specific total energy of a system. This word specific in thermodynamics means per unit mass. In other words, capital E is the mass times little e. By the way, when I introduce variables, I like to give their dimensions, which I use curly brackets to indicate. The dimensions of total energy are the dimensions of energy, of course, and the dimensions of specific energy are energy per mass. We'll usually work with these specific quantities, although in most textbooks they'll just call it total energy when they really mean specific total energy. You may recall from your thermodynamics class that E is equal to U plus kinetic energy plus potential energy, where U is the specific internal energy, not to be confused with the x component of velocity. Ke is the specific kinetic energy, and Pe is the specific potential energy. We write these out as E equal U plus V squared over 2 plus Gz. But as I said, we'll always be neglecting these potential energy terms, since we're dealing with gases at high speeds, where this term dominates this term. We can see from this term that E and U have the same dimensions as velocity squared, or in terms of units, which I use square brackets for, they're both meters squared per second squared.
Dude, how do you get meters squared per second squared from E or U?
Good question, Joe. I'll work on it on the side here. The units of E are Newton meters, the units of work or energy, divided by mass, kilogram, and I'll use a unity conversion factor. A kilogram meter per second squared is a Newton, and you can see that the kilograms and the newtons cross out, and we're left with meters squared per second squared.
Awesome, dude. Thanks.
You're welcome, Joe. I'll also define capital H as the enthalpy and little h as the specific enthalpy. So H equal m times little h. Again, from your thermo class, H is equal to specific internal energy plus pressure P times V, where this V is called the specific volume. It's just 1 over density. Thermodynamicists like to use V, specific volume, whereas fluid mechanics people like to use density. but they're related by this equation. And when you plug this into here, we get H equal U plus P over rho. This is the form of the enthalpy that fluid mechanics people like to use. Finally, enthalpy has the same dimensions as energy, and H has the same dimensions as little e, energy per mass. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.